For this lesson, I am going to teach you how to balance chemical equations. You may call these chemical reactions. Before we start, this is kind of an introduction to chemical reactions. We're going to start with balancing, and then we're going to learn the basic types of chemical equations in some later videos. And then I'm going to break those down one by one and teach you how to predict the products of a chemical reaction. But we're going to start with balancing, and this is one of our easier lessons. You can actually kind of think about this almost like a game. You really need very limited chemistry experience to be able to do these, and most students actually think they're kind of fun. So we're going to start by talking about the law of conservation of matter. You may have heard this called the law of conservation of mass. And what the law of conservation of matter says is matter is neither created nor destroyed in an ordinary chemical reaction. Now, you heard me say ordinary. I didn't have it in here as part of the definition, but nuclear chemistry is a little different, and sometimes students will say, well, what about nuclear? Because we actually destroy mass, and in nuclear we convert mass to energy. That's something totally different. So we're just looking at ordinary physical chemistry, and what I mean by we can't destroy matter is the matter that's here, and I just want you to think about Earth. The matter that's on Earth is here, and you know, you're not taking it to outer space or anything like that. Just think about what's here. When we, let's say, throw something away, we may have gotten rid of it. It's not in our possession anymore. We're not having to look at it anymore. But the question is, do those atoms still exist? And they do. They just may look differently. If I crumple up a piece of aluminum foil and I throw it in the trash, and then the trash gets carried off, it's out of my house, but really where are those atoms now? They may end up in recycling, hopefully. They may possibly end up in a landfill. When you put gas in your car, you know, we've all done this. We put gas in the tank and we drive around for a little while, and all of a sudden we're showing our tank's empty. We know it didn't leak out. Where exactly did those molecules that make up that gasoline go? Well, they've undergone the combustion process, and those individual atoms, those carbons and hydrogens and oxygens, still exist. They are just existing in a different way. It would be great if we could go out and catch all of them and put them right back in the gas tank, but that's not possible. They have changed during that chemical reaction. So the atoms themselves still exist. They just may look different. And I'll give you one more example. Let's say you burn a piece of paper. Well, you're not going to be able to use that paper anymore in the way that you were originally using it. Now it's just a pile of grayish black ashes. But those atoms still exist. Now, some of those atoms may be airborne now. Some of the atoms are sitting in the ashes, but you notice that you had a color change, had a lot of things going on to indicate there was a chemical reaction. But the bottom line is those atoms still exist. And that's why we balance chemical equations. A balanced chemical equation accounts for every single atom on both sides of the reaction. And when I say both sides of the reaction, I am referring to both sides of this arrow. So just real quickly to introduce you to a reaction, and I want you to think about a chemical reaction like a recipe. In a recipe, you add together this, and this, you know, whatever you're adding together, and you get certain things at the end. What you're putting together, those are your reactants. What you are getting, that's your product. And I think I have an example of that on some other pages coming up. But the parts of the reaction I want to point out are these. Your reactants are all the things that are on the left side. Think about these as your ingredients. These are all the things you're adding together. This arrow is the yield sign. You will often hear us say, this plus this plus this yields this. You may have one product, you may have more than one product, and different types of reactions are going to give you different numbers of products, and that's something we'll get into later. But when you hear me say reactants, we're talking about everything on the left, and when you hear me say products, we're talking about everything on the right. Now, I've listed the basic steps today for balancing a chemical equation, and you may want to jot these down before we get started. The first thing we're going to do is take an atom inventory of both sides. Those of you who have a job, maybe in retail, a grocery store, something like that, you've probably taken inventory before. And you know that means you are counting every single can of green beans you have, every single bag of chips by this manufacturer, every loaf of this kind of bread. When you take an inventory, you have to count every single thing of every single type of thing. So that's what we're going to do for both sides of the reaction. And then we are going to make what I'm going to call an educated guess to change the coefficients. Those are going to be the big numbers in front of the chemical formulas. We're going to make educated guesses and kind of say, I wonder what number should have gone here to make this math work out that I'm doing. And I'm going to show you how we do that math, because our goal in the end is going to be to have the exact same number of atoms of each kind on each side. For example, if I have 2 hydrogen atoms on the right, I'm going to have 2 on the left. If I have 4 carbon atoms on the right, I'm going to have 4 on the left. And honestly, just me explaining this to you is, I think, a lot more complicated than the actual process. So we're going to get into that pretty quickly. And at the very end, we're going to recheck our work by just looking at the atom inventory one more time. So that said, we're just going to jump right into how to balance chemical reactions. I'm going to point a couple things out before we do the first one. You'll notice I've got some blank lines drawn in front of my chemical formulas. That's where we're going to put our coefficient. That's the big number in front. Now, sometimes we don't actually have a number written here at the end, and that's because the understood coefficient is a 1. Like we often do in chemistry, we don't write 1s. So if you don't see anything in front, you would assume a 1. And what you're looking at here is an unbalanced reaction. Now, I've done a lot of these, so I can just kind of eyeball it, and I know it's not balanced. You will get better at that as you become more experienced in chemistry. But right now, it just looks like there's 1 of each of these, and I know that that's not possible for this reaction. So here's how we play the game. The first thing we're going to do is we are going to always divide our reaction in half at the yield sign. So right there at the arrow, you're going to divide it in half. And now you have separated your reactants from your products. And we are going to take an atom inventory of both sides. So that means on this left side, I'm going to write every atom that, that exists on this side. So I can see sodium, and I see chlorine, and I see fluorine. You notice we broke it down into 1 of each. Now, what I'm going to do to make my life simple is this list I just made on this side, I'm going to write it exactly like that on this side. That way I'm always comparing straight across. And now we're ready to do our inventory. So we're going to count how many of each atom we have on each side so we know what we're working with. I have 1 sodium, I have 1 chlorine, and you see that 2 right there? That means I have 2 fluorines. Okay? Now on this side, I have 1 sodium, 1 fluorine, and 2 chlorines. So now I'm just going to kind of step back and look at what I've got here. My sodiums look good. They're balanced on both sides, but I can see that my chlorines do not match and my fluorines do not match. Now I'm going to tell you there's not always a perfect place to start. You may decide, hey, I'm going to take care of these chlorines first, and your friend may say, well, I think we should take care of the fluorines first. Sometimes it doesn't matter at all. Sometimes it is better to start with one substance than another, and you literally just learn that from experience. In this case, I don't think it really matters which one to start with. I think I'm just going to go ahead and fix these chlorines. Now I've only got one chlorine on this side and I've got two. Right here is chlorine. So I'm going to ask myself, what number could I put in front of this whole molecule that contains chlorine that would make that be two chlorines? And I like to start with the lowest possible number, so I'm going to try a 2. Now here's what I really want you to watch and look at what I'm doing while you listen to what I'm saying. 2 times an understood 1 is now 2 sodiums. 2 times an understood 1 is 2 chlorines. When we put a coefficient in the front, that changes everything in that chemical formula. And what I like to do is once I've put a coefficient in front, I methodically work through that formula left to right, changing everything and making a note of that. Now, I fixed chlorines, but I actually messed up sodiums, and my fluorines are still wrong. So I think I'm going to go ahead and address sodium here. I've got 2 on this side and only 1 here. So I'm going to put a 2 in front. Now, 2 times 1 is now 2 sodiums, so I fixed that. And check this out. 2 times 1 is also 2 fluorines. By default, when I was working on fixing the sodium, I actually fixed the fluorine too. So it just happened to work out. So this reaction is actually 2 moles of sodium chloride plus 1 mole of fluorine gas yields 2 moles of sodium fluoride plus 1 mole of chlorine gas. I know I'm balanced because the sodiums match, the chlorines match, the fluorines match, and I'm done. So my students, when I tell you to show your work on these, this is what I'm looking for right here, and then this is your final equation. So let's look at another one. First thing we do is divide this reaction in half, and hopefully you've paused and taken a second to write this down. So now we're ready to take the atom inventory. On this side I have iron, chlorine, sodium, oxygen, and hydrogen. Got a lot of stuff going on there. I'm going to take this list and repeat it on the other side. I typically my list is always in order of the way I've read this first side from left to right, and then again you just want to repeat this list on the other side so you're comparing straight across. So I have iron, chlorine, sodium, oxygen, and hydrogen. So now let's count up how many we have of each on each side. So I've got 1 iron, and I'm just looking, that's an understood subscript of a 1. I have 3 chlorines, 1 sodium, 1 oxygen, and 1 hydrogen. Now, on this side, I have 1 iron, 1 chlorine, 1 sodium, but now I've got some parentheses here, and this is where you're going to need to be careful. This is not hard, you just have to pay attention. Do you see how this 3 is outside of these parentheses? That means you're going to have to multiply that 3 by this subscript and the 3 by this subscript. So if you have a number outside of the parentheses, you're going to multiply that number by all of the subscripts inside the parentheses. So I actually have 3 times 1, 3 oxygens. And I have 3 times 1, 3 hydrogens. So now we're ready to balance this thing. And again, I am just making educated guesses. Irons look good, so I'm not going to mess with those yet. This looks like a pretty easy place to go ahead and make a change. Anytime you've got any number of something on one side and just one of that thing on the other, That's always a pretty good place to go ahead and try to fix some things. So since I've got 3 chlorines here, I'm going to pop a 3 right here in front of sodium chloride. Now remember, that's going to change my sodiums and my chlorines. 3 times 1 is now 3 sodiums, so make sure you change that. And 3 times 1 is 3 chlorines. Okay. That really only fixed chlorine, but I think now I'm going to come over here and maybe fix my sodiums, because I've got 3 over here and I know I need 3 here. You didn't have to fix that one. It's just what I decided to work with. 3 times 1 is 3 sodiums. 3 times 1 is 3 oxygens. And 3 times 1 is 3 hydrogens. And all of a sudden I look at this and I realize, wow, I just fixed everything. My irons are correct, chlorines match, all of these match, and I am done. So sometimes you'll get something that looks kind of bad and you're like, oh gosh, that's going to be a pain. And you'll just change one little number and it'll fix like 3 or 4 things at once. So love those. All right, let's do another one. We divide it in half at the arrow, and now we're going to take our atom inventory. So I see aluminum, bromine, potassium, sulfur, and oxygen. And let's repeat this list on the other side. Aluminum, bromine, potassium, sulfur, and oxygen. Got a lot going on in this one, but we're not scared because we know this is actually pretty easy. So let's count up what we have. We have 1 aluminum, 3 bromines, 2 potassiums, 1 sulfur, and 4 oxygens. Let's take a look at the other side. We have 2 aluminums, and again, I'm just looking at that subscript. I have 1 bromine, 1 potassium. Now, sulfur is inside the parentheses, so that 3 that's outside, 3 times 1 is 3 sulfurs, and 3 times 4 is 12 oxygens. So everything here needs to be fixed. So I'm going to check it out and kind of decide maybe what I want to work with first. Let's see. I could try a 2 in front of this. And listen, sometimes I'm wrong. And if you're wrong, sometimes you just literally mark it out and you go back and you try something else. And that's just how you do this. So it is some trial and error. So let's just try a 2 here and see if that works. 2 times 1 is 2 aluminums. And 2 times 3 is 6 bromines. Okay. If I had that 2 correct, then it looks like to fix bromines, I'm literally going to have to put a 6 here. And that would be 6 times 1 is 6 potassiums, and 6 times 1 is 6 bromines. So I've got aluminums are good and bromines are good. Now, let's just take a look at these potassiums here. I have 6 on this side, and I only have 2 here. So what I'm going to ask myself is, what number could I put in front of this so that when I multiply this by this, you always multiply the coefficient by the subscript, that I would also have 6 potassiums on this side. So what times 2 equals 6? And I know that's 3. So I'm going to try a 3 out. Now 3 times 2 is 6 potassiums. 3 times an understood 1 is 3 sulfurs. And 3 times 4 is 12 oxygens. And look at that, that one number fixed everything else. My aluminums match, my bromines match, potassium, sulfur, and oxygen. So I hope that now you're kind of saying, hey, I'm getting the hang of this. Yeah, it's just kind of a balancing act. It's just Try this and see if it works. If it doesn't, try something else. So let's look at a couple more examples. All right, let's divide this one in half. I have phosphorus and oxygen, phosphorus and oxygen. So this looks like it's going to be pretty straightforward. I have 1 phosphorus, 2 oxygens, 2 phosphoruses, and 5 oxygens. So probably the most obvious change, right off the cuff, might be to put a 2 here. So, try it out, just see how that works. Okay, that really didn't take care of anything else. But I can see that I'm probably going to have a problem with that because it looks like something's going to have to go here. Because, see, I have an odd number of oxygens on this side, and I have an even number on this side. No matter what I put here, I'll always have an even number of oxygens on the left because I'm going to be multiplying by a 2. But over here, I'm only going to have an even number of oxygens if I have an even number in the front. So this could be a little bit weird, so I'm going to have to think about it. So maybe I want to try the smallest even number here. And that's 2 times 2. That's 4 phosphoruses. And 2 times 5 is 10 oxygens. Now, the oxygens are an easy fix because I can just pop a 5 right there, and 5 times 2 is also 10. But I can real quickly see the 2's not going to work out there. Maybe it would have been better if I would have just marked that out and put a 4 in its place. That gives me 4 phosphoruses, and now I'm balanced. A lot of students hate marking things out, like just having, especially if you're writing in ink, it drives me crazy too, but just know that is the nature of the beast on these particular problems, and sometimes you just have to mark something out and try a different number, and if you're doing that, you're doing it right. So don't let that confuse you or make you feel like you're not doing a good job. Let's look at the next one. So we're going to divide in half at the arrow. I have lead, oxygen, hydrogen. I got hydrogen right there too, and chlorine. So I only have to write hydrogen down once because you want one representative of each written down. But I will tell you this, when you're trying to fix hydrogen, you are going to have to be careful because are you fixing this one or this one? So when I have an element that's maybe in 2 different compounds on the same side, I'll usually just try not to even touch that one unless I have to, because sometimes fixing something else will take care of that for you. So hydrogen is probably something I'm just going to ignore for a little bit. Let's repeat the list on the other side. Lead, oxygen, hydrogen, and chlorine. All right, I have 1 lead. 2 times 1 is 2 oxygens. Now, I want you to pay real close attention to how I count these hydrogens. 2 times an understood 1, there's 2 hydrogens in this, plus 1 more here. So since you have 2 hydrogens in this compound and 1 in this one, you're going to add them together. I tell students just think about adding because you see a plus sign between them. So that's a total of 3. And chlorines are 1. Now let's take a look at the other side. I have 2 hydrogens, I have 2 chlorines, 1 lead, and 1 oxygen. Leads do not need any attention right now. I could start with oxygen, not touching hydrogen right now. I'm not interested in that, and I could work with chlorines. I will point this out though. No matter what number is in front of this hydrogen, you'll always have an even number here. That tells me there's going to have to at least be a 2 here. There's going to have to be an even number in front of this, or you'll never be even on this side. So just a little something to kind of tuck back in your mind as you work. I'm going to do oxygens first because oxygen's only in one spot here. I know it's going to have to be a 2. So I'm going to put a 2 here. 2 times 2 is 4 hydrogens. And 2 times 1 is 2 oxygens. So I fixed the hydrogens. Still don't want to touch these oxygens, so I'm going to go down here and see what I can do with the chlorines. I've got 2 here. I know I want 2 on this side, so let's put a 2 here. 2 times 1 is 2 hydrogens, plus you have 2 more here. 2 plus 2 is 4. Look at that. You just fixed hydrogens. Thank goodness. Now you're not going to have to worry about it. And 2 times 1 is 2 chlorines. And look at you. You finished it. Not nearly as bad as we thought it was going to be. And we're going to do one more example, and I may come back and do another tutorial on balancing equations later with just some different ones. So you can let me know if you feel like you're going to need more examples. You can drop a comment, or my students, you can email me and we'll get that done. But let's do one more here. I have barium, carbon, oxygen, hydrogen, nitrogen. I've already written oxygen down. Barium, carbon, oxygen, hydrogen, nitrogen. Okay, let's see what we got here. So I've got 1 barium, 1 carbon, 3 plus 3, I've got 6 oxygens, 1 hydrogen, and 1 nitrogen. Over here, I have 1 barium. Notice barium is not inside of the parentheses, so that's why there's only 1. I have 1 carbon. Okay, this looks like a hot mess because I have oxygen in 3 different things. I have 2 times 3, so I have 6 oxygens in this, plus 2 more, plus 1. So 6 plus 2 is 8, plus 1 is 9. I don't even want to think about that right now. I've got 2 hydrogens, and I have 2 times 1, 2 nitrogens. So I can tell you what I'm not going to touch, and that's oxygen. But bariums look good, carbons look good, so right here's where my attention's going to be. So I think the first thing I'm going to work on is the hydrogens. And you know what, I just noticed I didn't put blanks in front of these, so we'll just squeeze it in there. Let's put a 2 there. So 2 times 1 is 2 hydrogens. 2 times 1 is 2 nitrogens. Well, looky there, just fix that. 2 times 3 is 6 oxygens, plus 3 more is 9. And I'm finished. So sometimes the ugliest ones are actually the most simple ones to do. Now, there is one other thing I want to point out because we did not have any problems that presented us with this, but just on another page real quick, let's just pretend that on that barium nitrate that we just looked at, let's see here. I think this is very important to point out because you'll probably see it somewhere. On this barium nitrate that we just had, let's just pretend we would have ended up for some reason putting a 2 in the front. That would have caused us to have 2 times 1, 2 bariums. Nitrogens would have been 2 times 1, which is 2. And then you say that 2 times 2 is 4. Oxygens would have been 2 times 3 is 6, and 6 times 2 is 12. So what I tell my students is, when you're dealing with parentheses, take care of this business down here first. Multiply across the parentheses first, and then whatever you get, you multiply that by the coefficient. So take care of this first, then multiply by that. So again, on the oxygens, I said 2 times 3 was 6 oxygens, times 2 is 12. 2 times 1 was 2 nitrogens, times 2 was a total of 4. So when you're dealing with these parentheses, don't forget, last thing, to multiply by that coefficient in the front. None of our examples ended up having a coefficient in front of anything that was dealing with parentheses, so that's something I wanted to point out because you'll see that later. So I hope this was really helpful on balancing chemical reactions. Just remember, divide it in half at the arrow, list all the atoms present on the left, repeat that list exactly on the right, take an inventory. That means count up all of your atoms by looking at your subscripts. Remember, ones are understood. And then start making educated guesses. And when you make those educated guesses, what you are changing are the coefficients. The coefficients are these big numbers in the front. And I had on that very first page of notes for you, I said try different coefficients. So that is the big number in the front until you get it balanced on both sides. And also remember this, if it ever kind of gets out of hand and you feel like things are going off the rails and nothing's working, it's just getting uglier and uglier, start over. It happens to the best of us. Sometimes you might not have started in just that perfect spot and it'll just get out of hand really quick. Just take a deep breath and try it again. So I hope this was helpful. The next lesson coming up is actually going to be an overview of our 5 types of chemical reactions, and then we're going to break that down and go over each reaction type in an individual video.